Hi all, this is Claudio from expertfea.com with a new tutorial regarding the presence and use of smooth particle hydrodynamics. In ANSYS, they are called particle bodies. Let me share my screen. A short reminder about my website, where you can find lots of interesting things, beginning with tutorials, simulations, support, webinars, books, and so on. So regarding the use of particle bodies in ANSYS, we can see that this is a meshless free method, and it approximates the geometry. So it does not create finite elements. Yes, it is mostly suitable for where splashes occur or debris and shards. Yes, either for highly brittle materials or for fluids. It's very useful. Here we have lubrication and so on. So this being said, I opened ANSYS workbench. This type of let's say discrete in the explicit, only in the explicit dynamics scenarios. Let me double click, and before going towards the fluid simulations, let's firstly simulate something regarding brittle materials, and I was thinking about simulating a breakage of glass. So we're now for space claim to open. Any second now. So I was thinking about a ball which will be forced, will drop with an initial velocity onto a let's say window, a round window, yes. So let me create firstly the support, which I was thinking about being like an annular ring. So 250 here. And here 270. So this is the support. The glass that we will have will fall here, 100, or you know what, maybe even less. We need just to rest, all right? Just to be sure that we don't have here interferences. Let's round this maybe with 3 millimeters. All right, so now let's create a plane here and move it a little up with maybe 0.1 millimeters. And on this plane, we're going to create the glass that will be broken. Should we make it round, or should we? Let's make it round. I didn't simulate round glass until now. So it will go inside, hopefully. 300 diameter. It looks all right. All right, and how thick should it be? Maybe, I don't know, 3 millimeters. Let's see. Yes. Now regarding the ball, the easiest way is to create a sphere, but it usually, by default, it interferes and merges with the other bodies. This is why I have hidden these parts. And we need to somehow anchor it to something. This is why I left the plane. So the radius is almost 1 meter. Let's make it, I don't know, 80 millimeters. Now right click show. Okay, so it looks pretty nice. We're looking here to see how high should it be, something like this. Yes. We can even go with this even higher. We just need it to be like a ring. It's nothing so important. Let's look in the section view. Double click. Section mode. So we have the support, we have the glass, and we have the ball. I was thinking about making the ball smaller. Why? Because it will break here, and it will not be easy maybe to get through inside. I'm thinking about maybe it will get stuck, you know. The glass, it will get stuck between the ball and the cylinder. Just a little. Maybe 70, you know. So let's see here. Let's save this. This is a glass ball V1. Here we're going to name it glass ball V1. And keep in mind about the extension. Yes, it's native space claim, SCDoc, space claim document. We need to keep this in mind, maybe. We will see in the next minutes. Stream 16, today is February 11. SPH glass, and we're going to do also sloshing simulation. So our scenarios are, as you see, are very basic and quick to do. We want firstly to establish the fundamentals for my audience. So I double-clicked model here. Internally is opening ICE space claim, then it's importing it here in the mechanical window. F7 for full screen, and let's assign the materials. You know, it's a good time to assign the materials. Structure steel, let's leave it like that. But my advice is in Explicit Dynamics to always work with nonlinear materials. Here, and the glass explicit materials. It's not glass, it's called float glass here in this library. So here, as I said, nonlinear materials, I am deleting this default structural steel. Double click, yes, we have the materials refreshed. This is the, I will call it ring. This is the glass, and this is the sphere, which is ball. The ball and the ring you know what, they can also be rigid because we don't care about them. But let's see what solving time we get. Glass, float glass, and now the type of body, yes, will be particle. Now we're going towards the smooth particle hydrodynamics. So ignore my errors. Because I assigned here particle, it's mandatory. I can generate mesh, no problem. But it's not a particle. It's not a particle body. It's not mesh with SPH. This means we're going. Come on, what do you do? I need to access here method, and it's not possible. I don't understand this error. Okay, now it's possible. Let's select here particle. Again, it gives an error because I need to go back and select here particle reference frame. Now we have no error. Let's see, the default is, let's see the default diameter. Yes, this is the glass. Let's leave it like that at this moment. It seems like it's interfering with these elements. In reality, it's not, because the center of mass is the important, let's say, parameter or reference for this type of elements. So we don't care about contacts because we have the body interaction here. Let's save. And we're going to fix this ring. Control F for face, apply. And because we don't want to wait too much, let's just for fun assign standard gravity. I said just for fun because the end time will be so small that the gravity will not be so relevant, let's say, about minus y-axis. And how much should we wait? Let's put 0.01. And for now, we're going with these parameters, and we're going to optimize them as the tutorial goes. Yes, you'll see the tips, let's say, the important hints. So let me count these nodes, 4,500. And I said that we will assign a velocity here. It wants to be solid bodies. Control B for solid. And I want to assign components minus y. Minus y. So a small calculation is needed. For example, we're going to need for this ball to travel around, let's see here, maybe 150 millimeters, yes? So the calculation is like this. In order to run 150 millimeters in 0.01 seconds, this is what I prescribed as the end time, then in 1 second, how many millimeters will describe? This is what the initial velocity will be, yes? And x will be 150 millimeters if possible, always keep the measurement units 0.01 seconds. We reduce this and this, and we have millimeters. So easiest would be to go here. Let me show it to you. 150 over 0.01. So this is the speed, yes, 15 meters per second. 15,000 millimeters, yes. And the speed will be this one over here in 1 second, yes. So this said minus 15,000. Yes. Here, let's see some live results. And the sign, as usual, total velocity, strain, stress, and maybe a force reaction. Yes, in this fixed support. All right. Control S. Let's solve and see how long it will take. I purposefully left two details unoptimized because I want to see me how I'm judging, yes, this FEA. 2 minutes solving, yes, this is nice. Ooh. Yes, purposefully I let this detail, and I will let it solve for until the end because it's not a proper behavior, yes? And you will see what we need to optimize. Let's see for a second if it's someone on the stream. Nobody in the audience. All right, so we do have breakage here, but the deformation, let's say, is localized. We would have expected for some creases, for some cracks to appear. This means that it's not covering the, let's say, so well the reality of the simulation. Now regarding the stress, it's much nicer. But the behavior, we can say it's not correct. Let me show you what needs to be done. In a few seconds. We can also look at the energy summary. We want for the kinetic energy to decrease. Our glass energy, we want it to be almost zero. And the internal energy is increasing because we have lots of deformation. Perfect. It looks very nice. What time increment do we have? Very well. So the FEA just finished. Let me play it, save. Yeah, so something feels off. By the way, this is an animation bug. In order to solve it, we need to go here, show undeformed wireframe. So it only erodes what's in the contact here with the sphere. So the behavior of this glass plate is not correct, to say the least. Let's look a little here. Let's make 25 frames per second. So let's change a few of the parameters. Yes, this is kind of promising. We're going to duplicate it. The first simulation should close by now. With an error. It's an older version and I have installed more versions. This is why I begin to receive some errors. What I wanted to tell is here, I would like for the geometric strain limit not to be 1.5. Let's make it half at this moment, 0.7, and solve. I should have, and this is what I will do. I will not allow the small red points, maybe you know them, the center mass of the deleted elements. So let's make it here now, clear generated data, yes, solve. In principle, what I have done, I allowed the software to describe, to depict brittle behavior or fracture, let's say. By reducing the geometric strain limit. I think the impact is too fast. Should I make the ball bigger? Maybe I should make it bigger. So the speed is around 45 meters per second, which is pretty fast. Yeah, it's pretty fast when we forcefully strike this part. Let's ask, just for fun, let's ask someone what height corresponds to 45 meters per second. Let's see if the question is correct. 100 meters. So now I understand. It's too much. It's too much. So the geometric strain limit didn't help so much. Let's look. Yeah, the shards, the debris, they are going even much higher. the let's say, this pattern, 50 here. And you know what? Let's clear generate data and scope only the glass. Yeah, the height is too much. All right, so the height, the initial velocity. Let's go here and decrease it to hey, I said 15 meters per second. This is what I'm using. 11 meters. It's not so much. This is what I'm using here, 15 meters per second. Yes. So let's go here and make it maybe, I don't know, less. Or from 1 meter height, you know? 1 meter is almost 4.4 meters per second. This is 1 meter height. Look here. Yeah, it's roughly 1 meter. And as I said, I would like to increase the diameter of the ball. Instead of 80, maybe make it 90. Now it's 70 millimeters. Design, pull, no merge, and make it 90. Yes. What about 100? Let's make this transparent because I would like to pull this through the ring. All right, so it goes nicely. Save. Double click to update the geometry. Space claim is importing the geometry here in the mechanical window. Always delete what is extra. All right, this is nice. So 1 meter height, let's see. Clear generated data, solve. So while it's solving, let's see if we have any question from the audience. Yes, we have a question. A very respectful person. Aparihidunia, master. Oh, hi. One question, can I use particle elements in case of rubber expansion simulation? Yes. Usually it's not advised. Because I'll not explain now. Go on any chat GPT that you can find and see, but usually it's not advised. It's advised to use it for brittle or for sloshing for fluids. You will, however, for such high strain, you'll obtain very nice rupture or fracture of rubber. It can be done, but it's not what people usually do, but it can be done. It will work. It's no problem. It will work. So use it, test it, and remember to also ask ChatGPT or the same to understand what is the difference. Look here. So mesh-free Lagrange computational used to simulate free dynamic solid mechanics and complex continuum flows. Yes. Applications: fluid structure interaction, ballistics, volcanology, oceanography, where you have soil, sand, rocks, something. It easily handles extreme material deformation. Here is where your rubber should fit in. Fragmentation for the brittle and free surface flows. Limitations. Can be computational. It's not our case. But yes, remember to ask your GPT for more advice. Why does it take so long? Let's see how it behaves. Yeah, this is nice. Finally. I think the initial velocity is too low now. It's bouncing. Yeah, let's make it here. How many megapascals? Maybe 100 to easier see the cracking. Yeah, it's kind of bouncing. Let me increase this the speed, and also let's say that I told you that step by step we are going to investigate this. Let's almost half it, 0.3, and let's keep the velocity corresponding to 1 meter height. Save and solve. Yeah. Let's make a section plane. All right, so we can now look in the section view. Yeah, let's let it cook. Our preferred segment, we're going to watch other people simulating glass breakage. How to make glass in ANSYS workbench. Oh, let's see how to make. Let's learn. make glass. In design modeler, he's making a revolve. The shape glass. Okay. The drinking cup, the bullet composite. LS-Dyna. Let's see, is this pure LS-Dyna or ANSYS LS-Dyna? It looks like pure LS-Dyna from the rendering. Yeah, it's pure LS-Dyna. Yeah, it's very nice. It is a shell body. This is why they forgot to show the thickness. They should have left the thickness on. I think I met with one of these guys 2 years ago in Bucharest, I think, or in Brașov, in Romania. Yes, I think I met with them. We discussed about ANSYS LS-Dyna, and that was all. So here I think is one of my first simulations with glass breakage, but it's with a classic Lagrangian mesh. It's not SPH, it's not particle bodies. Yeah, it looks very nice. You see the thickness of the glass? Yeah, this is a solid body, it's not a shell body. Let's see our FEA, what it's doing. Come on. Do we need more? I think we might need more. A higher initial velocity. The breakage of glass, I think it's at around 250 or 300 megapascals. Yeah, I was way out. £4,000 per square inch to megapascals. Yeah. The FEA stopped, even though it didn't. It finished. Control S and save. It's sticking here, or what is doing? Let's increase a little. And I wanted to make it solve a little faster. Let's see if it's possible. Save. solve. You know, we don't want to wait 4 minutes. Let's make it 2 or 1. Who has the time to wait 4 minutes? I'm laughing because I know people that leave it for dozens of hours and they're using hundreds of thousands and millions of elements and nodes. Clear generated data, yes. This is a tutorial case, so we can use coarse meshing. Yeah, it's just for testing to prove a concept. Nothing happened much. The solving time didn't decrease. So where are we here? ANSYS glass. All right. Bending test of carbon fiber digital for glass. Glass fish tank. And what is this? Hydrostatic pressure? What? 9 years ago. Oh my God. And I thought I had a quartz mesh. This is a quartz mesh. It should be in the dictionary. Quartz mesh. Hydrostatic pressure. Yeah, who understands? Yes, knows. So, fixed support and the pressure. Oh my God, this is glass? If this is glass, why do you have this? You know why? Look here, 700,000 scale. 700,000 scale. Come on. This is CatFam, which are the OG, the original gangsters. This is made with SPH. This is smooth particle hydrodynamics, but in autodim. It's not ANSYS Explicit Dynamics, it's not LS9. And it's, 13 years ago. So it's kind of outdated, let's say. This looks very nice. VOF, volume of fluid, glass fiber. Not clickbait, gun quantitative. Glass plate. Oh yes, let's see. Oh, nice. Too bad it's a shell body. Please assign some thickness. But yeah, it's nice. I think I have seen more from this person. They switched to Abacus, I think, recently, yes. Yeah, they went from ANSYS to Abacus, I think. What is this? I don't know what it is, but it looks nice. Interesting. Compressing to kind of condense the what is here. Glass. Okay. Yeah, this is my first simulation made with SPH with glass. I had to make some support, so You see here tensile extension, and here is the rotation, of course, the torsion, and here is the bending. With finer mesh now. In section. Here's kind of 3-point bending, let's say. Okay. Yeah, it was made 5 years ago. I think they implemented in ANSYS, they implemented SPH in 2021, I think, or maybe 2020. So I kind of know the particle bodies. I know them from the beginning, and they had some limitations at the beginning, but now they are, let's say, easier to simulate. There are no more problems. Yeah, nice. Where are we here? 46 seconds. Yeah, it's too much. You know what? I'm thinking maybe the fact that I have one sphere per thickness, maybe it's not so useful. In principle, for proper bending of shell or membrane parts, let's say, we should have at least 2 elements per thickness. Maybe this is the problem. Yeah, it's not stiff enough. What should we do? I can make, and let's make the glass thicker in order to accommodate 2 layers of particles per thickness. This will almost double the solving time. But you know what? Let's do it. Then we're going to move towards sloshing. So let's grab this face and move it. How much should we move it? Three millimeters, 3.5. So it should go like this, all right. Right-click, update geometry from source. And while it's importing, I'm going to read if there is, yes, there is. There's a thank you. Yes, you're welcome. Good luck. So let's review the contacts again and delete them. Right-click, generate mesh. Yes, 2 elements per thickness. Now we should be better. We should have the proper stiffness in the glass. Of course, we need to greatly increase the velocity. Because we increase the thickness of the glass. Just for fun, what if I make here 1 in minus 6 seconds and here 10 maximum part scaling, save and solve. Ah, yes, instead of 4 minutes, 2 point something, okay. So, low velocity glass to beam path. What? What is this? This was made 1 month ago. Yeah, it looks nice. I like this breakage. Look at the time. Yeah. Yeah, according to me, it's a nice simulation. It's like it. Do you have something more? He has more. Simulations without context. Yeah, we like simulations without context. And here, I wanted to see this. Ooh, it's breaking so nice. Finally, someone who understands the breaking of brittle parts. Yes, this is beautiful. You see how annoying they are? This one, retain inertia of eroded material. He left it yes, maybe he doesn't know how to switch it off. And yeah, it's pretty annoying, yes. But nevertheless, it looks nice. Look here how annoying it is. Miss. It's like a bullet through chain mail, through armor. I did for fun. Yes, we like fun. This looks, yeah, it looks very nice. And here with the very high speed, yes. Here is the, he explored the explosion here. Yeah, this is nice. He explored, he wanted to simulate milling here. but yeah, with no success there. And here, what? Yeah, maybe an error. Abusing a physically accurate apartment in Blender. We don't care about Blender at this moment. Let's see how it works here. Oh, finally what we wanted. Finally. Yes. This is what I wanted. Yeah, so beware of the thickness. Yes, and this is how I wanted to correlate the diameter of the sphere with the shards that will break. Save. Yeah, it looks so nice. So where were we here? The speed should be, and I want it to be in meters per second, and maybe, I don't know, 20. Yeah, this is how it should behave. Look here, yes. Complete success. 0.25. And here the red points are not the inertia points that we switched on. These are shards, yeah, glass particles. And the stress, oh, it looks so nice. Let's make the stress in megapascals. And maybe assign 200 here. Oh, it's so nice. So here is an example of using SPH for brittle fracture. Force reaction and in the fixation of the ring. So, complete success. Let's go for the sloshing now. Sloshing. I will name this to be published because I'd like to publish it on my website. Here I get the same error, all right. Let's drag and drop another Explicit Dynamics and let's start from scratch. I will make a tank with 2 baffles and yeah, with water inside. Do we have something from the audience? Yes. Just a stupid question. There are no stupid questions. Come on. How do you see digital twin where NVIDIA and Google bringing physical data into digital? Would they replace this current FEA style analysis? Sincerely, I would say that it's like a normal step that will follow. A digital twin, if it's based on having scanned the real parts, having real dimensions, if the materials and the proper boundary conditions are assigned, I think it might replace the current simulation, the current or the past simulation trend. Digital twin, the twin evolved in the last years, and it's very promising. And it brings the immersion, I don't know, the reality of the geometry, let's say, coupled with, if possible, coupled with the proper behavior of materials and boundary conditions, in the next years will improve. The FEA and other similar. boundary element method and other methods, numerical methods, and there are chances that it will replace in the near future. Digital twin and a scanned world, these are, I would say that these are the future. Yes, it can be. I said that we're going to model a tank with some baffles. How should we make the tank? Let's make an axis, This is an axis. And on the end of this axis, let's make the 1 meter tank. Let's make it 1 meter. All right, move with control pressed. I will move it like this. 1,400. All right. Now let's drag 2 lines here and here. Let's trim what we don't need. We don't need this and this. And why did I make it full? Why did I make it full? Why? All right, let's offset what we have now to assign like a thickness, this one. Something like this. I don't know. 35. Okay. Now we need to make these small lines. This one, the thickness, escape, and also this one. Thickness. All right. Let's rotate what we have here. Pull, revolve, axis. It asks for an axis, and we're going full pull. This is the tank. Either you like it or not, this is the tank. All right, let's create a plane. And on this plane, we're going to make those baffles. 2 baffles, not to overstay our welcome. We'll make them in the easiest way, just a rectangle, something like here, because the thickness was around 35, let's make this maybe 30. Yes. And I promised 2 baffles. Let's make this transparent. Triple click 1, 2, 3, and we can move it. This is one baffle. 900. With control pressed, we'll move this here. 800, let's say. 1500. 1600. 1700. Yes, these are the baffles. Now, let's make it a little quirkier. So this means I'll pull this here. Yeah, and here let's do the opposite, yes? Something like this. If you don't like my baffles, I don't know what to tell you anymore. Yeah, let's test it. Let's test it. So design, combine. Let's cut this with this. Yes, and let's remove this and this ring, and we'll keep what's inside. Let's do the same thing again. Let's cut this with this. Let's remove this and this. And here, if we are going to rotate this coordinate system and plane in section mode, here are the baffles. All right. Now, I want to make the water. How should I make the water? Let's hide these, the baffles, and let's make the water inside. Sketch on this plane. Sketch. All right. One. Can I project this curve? Not this one. This one. And this one and this one. And let's set for a level. Yeah. So let's have something like this. All right, and now we're going to trim here, 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 and this will be the water. But the water will be revolved only 180 degrees. Yeah, here. So I will, with control pressed, I'm selecting this surface with control pressed, revolve. I will click the sketch and tell it pull both sides, no merge, 180 degrees. Why did I leave a space? Small question. Can I select this face and hit delete? Yes. Will we have two parts? Yes. Let's click this tank and hide it. Let's see if we can merge these two parts. Design, combine, select one with control pressed. We click the other one. This is the water. Right click, show all. Yeah, let's lower a little the surface of the water. Yes. Control S to save. Water tank sloshing V1. Caps is activated. Caps lock. All right. Let's unite the baffles. Combine the tank with the baffles. With control pressed, we select what we want to combine. So look in section view. In section view, we have the tank with the baffles, same part. We only need now to extract the baffle from this water. Yes. So look here, combine again. The target is the water. So with control pressed, I'm selecting the water, or I can select the water from here, no problem. And it will be cut with the tank, which will cut this with this baffle, yes? What we need to reduce, click regions to remove. I will remove this one. This is former water, yes? Escape and look in section mode. Look here, so it's correct. This is water, water, baffle. And now we will have kind of two waters. This is water and this is water, yes? This is the tank. All right, let's double click and assign the load for the tank sloshing. Any question? No question. Okay. All right. Let's assign some materials, you know. Structural steel. Do we keep the structural steel? Let's keep it. But you know, for the sake of this solving, let's keep it. Explicit materials. I'm going to assign the water. So this is the tank. This is water 1 and this is water 2. Water 2. All right. Water is water and the reference frame particle. The tank is made of structural steel. We can also make it rigid, but not today. Right click generate mesh. Let's make a section view. Something like this. I think it should have been done something like this. Yeah, something like this. So this is the water. But I want the reference frame for the two water domains to be particle. Right click generate mesh. We have water. How many? 17,000. All right. Let's assign some boundary conditions. How many steps? Let's make 1, 2. 2 steps. Is it enough? Let's make it 2 steps, yes. And here we'll make step 1 0.01. Is this one 0.02 and step 1 0.01. Automatic mass scaling, yes. Let's make it here 1e minus 6 10 maximum par scaling. here we'll leave it like this. No for inertia nodes, output controls, 100 result numbers. All right, so let's keep the standard Earth gravity minus, you can see it downwards, my plus x. And here, let's displace the tank. Control F for the surface. On the Z, how should we do it? Or like this, or like this. Let's go on the minus. Tabular. Minus how much? Minus 500? Let's see if it works. And here we're going for I don't know, 250? Let's see. Deformation stress, right click, switch to automatic mode, solution, total velocity, strain and stress in the tank, and probably maybe something like force reaction in the displacement. Control S to solve. Let's see a little. All right. Yeah, it should be nice. How many minutes it will take to solve? Yeah, we can live with this. 10 minutes? Yes. So again, ANSYS glass. All right, we don't see any ANSYS glass because, of course, except 1 or 2 persons, almost nobody is approaching the brittle fracture. This is something I was doing for windshield. So here is a sandwich, yes? Glass, glass, and PVB in layer. The shards, the debris, they are not falling out because they are held by the PVB interlayer. Yeah, it looks nice. We'll look at this one and then we're going for sloshing. This is very nice. So let's go for sloshing now. Oh, this is nice. Any question now? It's so nice. We are doing it with CFD. Sincerely, I'm interested in sloshing with SPH, with particle bodies. will look here a little as soon as we see how the FEA works. Oh, yes, it looks nice. Yes, it's promising. What do we have here? Yeah, nice waves. Yeah, nice. But no SPH. Only, of course, what I have done. This looks nice. Yeah. Oh. And this is the Eulerian Lagrangian here. Arbitrary Lagrangian Eulerian here. So it's not SPH. This is Eulerian Lagrangian in ANSYS, just for you to see the difference. Yeah, we don't have the small spheres. When doing such simulation with solid bodies, there are leakages. You can see, yeah, parts of the water, they are kind of leaking through the tank. In other frames, yeah, here you can see it. This is Eulerian Lagrangian approach in ANSYS workbench explicit dynamics. Yeah, it can be done. SPH finally, but it's not ANSYS workbench. LS Dyna is not for beginners, you know. It requires lots of knowledge, and it has a steep learning curve. Yeah. Mr. Dennis Chan. Yeah, he has nice things. Am I subscribed? Now I'm subscribed. Dennis Chan FA, DC FA. Yeah, nice. I'll look more offline when I'm not on live stream. Of course, you cannot look on YouTube offline. Thanks, Sloshing using ANSYS UFX. Here is Aqua. All right. what I'm doing today now. This looks nice. Here is a SPH with a bearing to simulate lubrication. I've done it 2 days ago. This is nice. Mr. Amin Topa is a guru in LSD, no? Yeah, it looks very nice. Ah, okay. Mm-hmm. It takes a while. But it looks nice, you know? There is some leakage here, but it looks nice. It's worth the waiting. So, sloshing velocity SPH. Very nice. And here is, yes, aquaplaning. I have also simulated aquaplaning. Also with SPH, if I remember correctly. Yes, here. So this is the version with coupled Eulerian Lagrangian. It was made 7 years ago. This is with coupled Eulerian Lagrangian. And here it's the version with SPH, with the smooth particle hydrodynamics. Yeah, very nice. Done more on this wave generator. This one is interesting. 2 water droplets impacting. Let's see what is here. 10 more minutes, come on. So 2 water droplets, yes? We have the bigger one is static, and the smaller one, which is heading towards the bigger one. The smaller one, it's fusing, it's merging, it's kind of dissolving into the bigger one. This can only be done with SPH. You cannot use other mesh to simulate such case. Yeah, we had this for concrete, I think. Yeah. Breakage. I signed iron for the hand. Sand. So this is a very good application for sand, to use particle bodies. Here it's a cute simulation. A sleigh crashing into a snowman. It's nice to have fun. Here is like a asteroid impacting a portion of the planet I made at SPH, and this is the behavior with the crater here. Yeah, it's nice. And here is one of my most, I like this most. I worked very much on making it with coupled Eulerian Lagrangian, and it stopped, it didn't work. But it worked with SPH, with particle bodies. It was a lot of work. excavation here. Yeah, it's very well suited for soil simulation. Another look, 7 minutes. Feel free to fast forward, skip until you see the results that you like. So I will stay until the end. Here is something. Here is something that I took inspiration from Lensmore, Japan. I will show you in a few seconds. We have lots of leakage. I think because this mesh is too coarse. If I had the mesh finer, I think I wouldn't have had such leakage here. We cannot do something like this with another type of element. Only SPH should be used. So let me show you the original idea. Because I also want to show you an extended, let's say, library database repository for SPH. These Japanese colleagues are using SPH very much. This is kind of like SPH, but it's discrete element. Let me find some SPH. Of course, you cannot find it when you are live. It's the Murphy's law. Here I think we have. So I took, from seeing their results, I took inspiration to perform my own simulations. Here is SPH, yes. Here, let's look here, the fracture of glass. Here it's a mixture, I think. Yeah. Here I think is a thing that only LS-DYNA has. It performs a transition at the breaking point. At the breaking regions, it forces the solid to become SPH, a particle body. At the breaking point, maybe. This is what I'm thinking about when I say adaptive solid SPH. Here is the... yeah. Breaking of glass during torsion. Adaptive solid to SPH. Yeah, it seems that the Lagrangian elements become smooth particle hydrodynamics. It's so nice, it's nirvana. What do they have with SPH? Particle and spouting. Not so interested. This is DAS. DES. Let's see some DES. Discrete elements. Yeah, they can color it differently. I don't. ANSYS we cannot color the mesh or the SPH. Yeah, very nice. We can only be inspired by our Japanese colleagues. I think we're approaching the rain. Oh, hourglass. This is something that I would like to simulate in the future. The sonic boom. This is what we don't have in SPH Dynamics. We don't have like an inlet, an injection point with a specified mass flow to inject SPH, to inject particle. This is what we don't have in SPH Dynamics. It exists in LS Dyna, but not in classic SPH Dynamics. Hourglass using DS. I'm wondering if it can be done with SPH. I think it can be done. Assigning sand as a material, yes, it can be done. All right, SPH. I think this can be done with SPH. Right-click, translate to English. Yeah, this is something they have done in the beginning. They have evolved very much in the meantime. This is what I would like to do next. Machining with SPH. I will do it in the recent future. Here, and here is where I took the inspiration for the umbrella, for the raining. What I came up with additionally with the tray in order to catch the rain. Is this SPH? Let's see. No, it's not SPH. So we have finished here the simulation. Save. It looks so nice. There is some leakage, I guess, due to the quartz mesh used in the tank. All right, the stress is high in the tank because I didn't use a nonlinear steel. I used the default steel. So I always advise NetSuite engineers to use nonlinear materials. This is the first reaction in the display, which was applied on the entire body of the tank. And you know what? Let's also do one without section. This one. Let's make it 10 meters, and this is how it looks like. Yes, that error that I told you, which is solved by going here, show undeformed wireframe. Yeah, it looks so nice. So this is all from my side today. We have learned lots of new things regarding SPH. I don't have additional questions, so have a good night and good luck in your simulation career. Bye-bye.